So let's look at Chapter 17, Electrochemistry. In this chapter, we're going to review redox reactions. We're going to look a little tiny bit at oxidation numbers or change of oxidation states. In terms of balancing redox reactions, I'm going to let you do that on your own. We're going to consider galvanic and voltaic electrochemical cells. We're going to look at how we can get a potential for a cell, calculate delta G naught and K. We're going to look at electrolysis and electrochemical cells off of standard state, and you're on your own for corrosion. So we can look at reactions and frequently tell whether or not we have oxidation and reduction. Sometimes it requires assigning oxidation numbers or oxidation states, and sometimes it's really pretty obvious. If we take sodium and react it with chlorine and make 2 sodium chlorides, we go from an element into a compound. And if you go from an element into a compound, doesn't matter which side either is on, you're almost always going to have redox. We remember that oxidation is the ox part of redox, and this is loss of electrons. We know that reduction, which is the red part of redox, is gain of electrons. We know that these guys cause each other in the sense that by something gaining electrons, it is removing electrons from something. So oxidation and reduction work together. In this case, sodium is going from a neutral element with a 0 charge into a +1. Therefore, it's losing electrons and it's being oxidized. Chlorine is going from 0 as a neutral element into -1. It's gaining electrons and it's being reduced. Now, sometimes it's not quite as obvious. Now, here we do see it's going from an element into a compound, but we don't necessarily see the change in oxidation states. So go back and review in Chapter 4, where we realize that when we have hydrogen with a nonmetal, it's going to have an oxidation state of +1. When we have oxygen, it's almost always -2. When we go from a neutral element into a -2, it's going to gain electrons. Gain of electrons is reduction. Hydrogen is going to go from 0 into +1, so it's going to lose electrons, and that is going to be oxidation. And they're going to work together in a redox reaction. So what does this look like? Well, first of all, we're going to look at a standard galvanic cell. Now, standard, again, is one of our baselines. Standard means 1 molar and 1 atm. Standard, again, like with the standard states back in the previous chapter, doesn't imply a temperature, but with pretty much without exception, we're going to work at 25 degrees Celsius for these reactions. And when we do an electrochemical cell, we have to have 2 parts. And we draw these out as beakers. And if we draw them out as beakers, we're going to do an oxidation half and a reduction half. Now, the oxidation half is going to be the half that contains the anode. The oxidation is where the electrons are going to come from. Here, the reduction half is going to be the cathode, and this is going to be our cathode here. And what we're going to have, since we're working at standard state, 1 atm and 1 molar, is we're going to have 2 reactions, and we're going to break these into half reactions. So on the left, in our half reaction, we have copper losing electrons to make copper 2+. That's going to be -2 electrons. Those electrons in our reduction half are going to be gained silver to go into Ag. And these 2 half reactions are going to make up my standard electrochemical cell, where the one losing is going to be the oxidation half, and that will be our anode. The one gaining is going to be our reduction half, and that is going to be our cathode. In order for this to occur, we have to have 2 more parts. We have to have the wires that hook these together, and we have to have electrons or ions flowing to complete our circuit. If our half reactions, which is what we call these pieces up here, contain solid metal, they are going to be our electrodes. So in this case, our solid neutral silver and the solid neutral copper will be our physical electrodes, the wire in place. And we're going to attach our 2 beakers that contain our solutions. 1 molar copper 2+ and 1 molar silver plus is going to be attached with a salt bridge. That is simply to complete the circuit, so the counter ions are going to flow. If the electrons flow spontaneously off of the copper wire, making more copper 2 plus through the wire and go and collect on this electrode. And these electrons are picked up by the Ag plus in the solution. And this is spontaneous. The cell is said to be galvanic or voltaic. If the cell is not spontaneous, then it is said to be an electrolytic cell. So we can describe whether or not this can occur, whether or not these electrons can move from one side to the other by either the cell potential, which we measure in units of volts. By the way, a volt, by definition, is a joule per coulomb, coulomb being a unit of charge, joule being work, or we can call this an electromotive force. So this is a driving force for a reaction. We can measure it with a voltmeter, and you're going to see it listed as the potential, the volts, or the EMF, electromotive force. So what do? If we are looking to draw the electrochemical cell, so again, we have two portions for this. Anytime we have electrochemical cells, we have to have oxidation and we have to have reduction. Oxidation is where the electrons come from. Reduction is where the electrons go to. The oxidation half is always going to be on the left, and that will be our anode. The reduction half is going to be on the right, and that is going to be our cathode. We're going to dig up the reactions as we see them and see whether or not electrons flow spontaneously. Again, if they do, electrical work is available, and we have a galvanic cell. We tabulate whether or not these reactions occur spontaneously compared to what we call the standard hydrogen electrode. Standard hydrogen electrode is shorthanded as the SHE, standard meaning 1 atm and 1 molar, meaning we have 1 molar H plus, 1 atm of H2, and this is defined to have a potential of 0 volts, and all other reactions are compared to this one. Now, when we do this, we list them all as reduction, which means they're all going to be something gaining electrons, making something else. And the potentials will go from the most positive down here up to the top to the most negative up here, meaning the most spontaneous at the top and the least spontaneous at the bottom. So starting up here on the standard reduction potential, these are 25 degrees Celsius. This is nowhere near a complete list. The first reaction we see is fluorine. We know that fluorine is very spontaneously going to gain electrons to make 2 fluorides. Our reaction continues and then starts back up over here, and the least spontaneous is lithium. Lithium gaining 1 electron to make lithium as a solid has a negative potential. This is an extremely non-spontaneous reaction. So this is the most spontaneous. This is the least. And what we're going to look for overall for a spontaneous reaction is an E naught for our overall electrochemical cell to be a positive value. If the E naught for our cell is positive, then our reaction is spontaneous. And we have ourselves a galvanic or a voltaic cell. So we're going to have these tabulated. Frequently, they're listed in one straight line here where you would have your fluorine reaction on the top, the corresponding voltage over here, the least spontaneous down here is the bottom. And what we're going to do is we're going to have two portions. We have to have an anode and a cathode. We know anode is where oxidation occurs, and the electrons are going to come from the anode, making this the negative electrode. Cathode is where the reduction occurs. Electrons are going to go to the cathode, and the cathode is going to be positive. If we look at our chart, we're going to have two potentials. We're going to have a oxidation and a reduction. What we do is we read our potential straight off this chart, and we say that the E naught, the potential for the overall cell, is going to equal the potential of the cathode. So here, this is our potential. The naught means standard. Cathode is going to be the first at least for a galvanic cell, will be the first reaction that we find. And then we are going to subtract the potential at the anode. So as we go down and we look at this, the first reaction we find we're going to have is our cathode. The second reaction we're going to find will be our anode. We're going to take the potential at our cathode, subtract the potential at our anode, and that will give us an E naught for the cell. If we do it in this direction, our potential will always be positive and our cell will be spontaneous. Let's do an example. So we're going to look at half reactions. So we want to have a cell between copper and silver. So if we look at our cell potentials, what we're going to find is copper 2 plus aqueous plus 2 electrons goes into Cu as a solid, and we're going to find Ag plus aqueous plus 1 electron goes into Ag as a solid. And these are our half reactions. Note I have written them both as reduction. Something is going to have to be oxidized and something is going to have to be reduced. So one of these reactions is going to have to be backwards. The question, though, is let's assume that what we want is a galvanic cell. And with our galvanic cell, the reaction at the cathode will be the first reaction that we find on our table. And then we will subtract the reaction at the anode. So the first thing we have to do is find these guys on the table. So if we go down our table, we go down here and then we come over here and go down again. The first reaction that we find is Ag plus an electron goes into Ag as a solid. So this is going to be our cathode. And then we see if we can find some copper. So we keep going and we find Cu2 plus 2 electrons goes into Cu. So this is going to be our anode. And to calculate what the force is or the potential, we're simply going to take E naught at the cathode, subtract E naught at the anode, and the E naught for the cell is simply going to be 0.80 potential at the cathode minus, right here, 0.34 volts, which is the potential at the anode. When we finish the math on this one, we're going to get E naught is equal to a value of 0.46 volts. This is positive. This makes the reaction or the cell spontaneous or galvanic. Now note, I do agree that we wrote two cell potentials both as reduction. We took the value of the one at the cathode, subtracted the value of the one at the anode, but yes, there were still both reduction. But by taking and subtracting the potential of the anode, what we did by subtracting it is a reverse the reaction and we made it oxidation. So in a sense, this minusing the E naught at the anode effectively flips the reaction and adds. But it seems to be easier to teach it as the first one you find, subtracting the second one you find, rather than flipping and adding.